Good evening students, welcome to GDC classes. We are back with our another video lecture on medicinal chemistry. So without wasting any time, let's start with our today's lecture on beta-lactam antibiotic. Now this lecture is the continuation of our last lecture, that is on beta-lactam antibiotics. Now there we have already completed penicillin. Now in this video we will continue with our second beta-lactam, that is the cephalosporin. Okay, now what is cephalosporin? Now this is a beta-lactam antibiotics that is structurally and functionally similar to penicillin. Okay, now this is the semi-synthetic antibiotic that have a broad spectrum of activity when it is compared with the penicillin. Now cephalosporin are the derivatives of 7-amino cephalosporanic acid. Now when we talk about the penicillin, now penicillin was having a 6-amino penicillinic acid. The penicillin was the derivative of the 6-amino penicillinic acid. Now when we talk about cephalosporin, it is a 7-amino cephalosporanic acid derivatives or 7-ACA. Now the cephalosporin are bactericidal in nature. Now as they are bactericidal, that means they will directly kill the bacterial cell and will have a irreversible action. Okay, now talking about its structure, now it has a beta-lactam ring that is fused with the tetracyclic ring dihydrothiazine. Now what is this dihydrothiazine? Now it is a 6-membered ring in which one carbon is replaced by the thiazine group and the other carbon is replaced by the nitrogen group or the azo group. So dihydrothiazine. Okay. Cephalosporin has a basic moiety called as cephin in its structure. Now when this beta-lactam joined with this dihydrothiazine ring, together they are known as cephin. So they have a cephin as a basic moiety in its structure. Now this cephalosporin is isolated from the fungus Cephalosporium acrimonium in 1948. Okay. Now in the structure of the cephalosporin, the R1 and R2, whenever we make any changes in these position or we modify these position, the structure or substituents in this position, we get different cephalosporin derivatives which have different antibacterial properties. Okay. Now moving forward towards the mechanism of cephalosporin. Now cephalosporin also has the similar mechanism as the penicillin, that is to inhibit the cell wall synthesis of the bacterial cell. Okay. Now this cephalosporin, they bind to the penicillin binding protein. Okay. Now when they bind to this specific penicillin binding protein, they inhibit two enzymes, that are the transpeptidase and the carboxypeptidase. Okay. Now these two enzymes are responsible for the cross-linking between the peptidoglycan chain. Okay, between the peptidoglycan chain. Okay, the cross-linking is due to these two enzymes. Now as they are inhibited by the cephalosporin, that means the cross-linking will not happen. So as the cross-linking will not happen, so the cell wall will also not form. So as the cell wall is also inhibited, so the bacteria will be without cell wall. So it will not be able to survive and it will get killed. Okay. Now moving forward towards the classification of these cephalosporin drugs. Now these classification is based on the generation. Now as we move on from the older generation towards the newer generation of cephalosporin drugs, we have some add-on property, plus we have some side effects too. Okay, now in this different generation drugs, we have some oral drugs and some parenteral drugs. Now these parenteral drugs can't be given orally due to the acid instability. Now, as these drugs are unstable or instable in the acidic environment, so they get degraded by the acid that is present in the stomach. So, they can't be taken orally. Okay. Now, moving forward towards the structures or the particular drug we will discuss here. Okay, the first drug is cefazolin. So this is the first generation parenteral drug. Now as it is parenteral, so it will be acid unstable. So it will get degraded by the acid that is present in our stomach. Okay. Now this drug is particularly effective against the gram positive bacteria. Okay. Now it has a very limited action towards the gram negative bacteria. Now this particular cefazolin is effective against the methicillin susceptible Staphylococcus aureus. Now what is this? This is the bacteria. Now this bacteria is susceptible for the beta-lactam antibiotics. That means it can be killed using the beta-lactam antibiotics, but still it can cause infection to the body of an individual and can make the individual fall sick. Okay, so this bacteria need to be killed, and we can kill it using this methicillin or the beta-lactam antibiotics. Okay, now this cefazolin does not do not act against the methicillin resistant Staphylococcus aureus. Now what is this methicillin resistant Staphylococcus aureus? Now this particular bacteria is not susceptible for the beta-lactam antibiotics. Most of the beta-lactam antibiotics cannot kill this particular bacteria. So the cefazolin is also not effective against this MRSA. Okay, now moving forward towards the structure of cefazolin. Okay, now cefazolin is a cephalosporin derivative. So it will have a Cephin moiety as a basic moiety. So here we have a beta-lactam ring that is fused with the dihydrothiazine ring. Okay, now at third position and at 7th position we have the substitution change here, which decides that what type of cephalosporin derivative it will be. Now at third position it has a thia, that is a sulfur group that is joined to the heterocyclic ring further. Now here we have a amide group that is joined again to the heterocyclic ring which is 5-membered, and it has a 4 azo groups. Okay, and a 1 carbon attached. Now second is the cephalexin. Okay, now cephalexin is also a first generation cephalosporin drug and it can be taken orally. So it can be taken orally, that means it will have a good solubility and it will be acid stable. Okay, now it is effective against the gram positive bacteria and some gram negative bacteria, not all but some. Okay, now it is also effective against the methicillin susceptible Staphylococcus aureus, but it is also not effective against MRSA. Okay, now moving towards its structure, it will also have a Cephin moiety. Okay, now at third position it has a methyl group, and at 7th position it has a carbon that is attached with the amino group and a phenyl ring. Okay, Now it's a very simple structure, easy to remember. Now the third drug, we have a cephalothin. Now cephalothin is the first cephalosporin drug that was marketed in the year 1964. Okay, now it is also a first generation cephalosporin drug. Now this drug is given parenterally. Now moving towards its structure, it also has a beta-lactam ring that is fused with the 𝘂𝙎𝙎𝙎𝙎 ring. Now at third position, it has an ester group attached. Okay, at seventh position, now starting from its name, cephalothin. So from thin, we can remember that it has a thiophene ring in its structure. So here at seventh position, amide group, and that amide group is attached with a side chain that is a thiophene ring. Okay. Now moving forward towards the next drug, that is the cephalosporin. Now the cephalosporin is the Zwitter ion. That means it contains both the positive and the negative charge in its structure. Okay. Now this is particular cephalosporin drug is now not used very widely in humans as due to its severe side effects like nephrotoxicity. So it is also banned in many countries due to its severe side effects, and basically it is used in veterinary practices now. Okay. Now moving towards its structure, now it also has a beta-lactam ring that is fused with the dihydrothiazine ring. Now its name we have cephalosporin. From ridin we can say pyridine. So it has a pyridinium ring in its structure. Now here we have a pyridinium ring at the third position, and at seventh position again we have a thiophene ring. Okay. Now moving forward towards the next drug, that is the cephedrin ring. Okay. Now cephedrin, now it is also a first generation oral drug, and it also works against the methicillin susceptible Staphylococcus aureus. Okay. Now moving towards its structure, now it also has a beta-lactam ring that is fused with the dihydrothiazine ring. Now at third position it has a CH3 group attached, that is a methyl group attached, and at seventh position again with the amide group we have a carbon with the NH2 and a phenyl ring. Okay. Now moving forward towards the next drug, that is the cephadroxyl drug. Okay. Now cephadroxyl drug is the first generation cephalosporin again. Okay. Now it has a very strong activity against the gram-positive bacteria and a moderate activity against the gram-negative bacteria. Okay. Now it has an excellent absorption, and it has a longer half-life. That is, it can stay in our body for a longer period of time and show its action for a longer period. Now moving towards its structure, now it also has a Cephn ring, that is the beta-lactam ring that is fused with the dihydrothiazine ring. Now again at third position we have a methyl group attached, and at seventh position along with amide we have carbon with NH2 and a phenyl ring that is attached to the OH group. Okay, so cephadroxyl. Okay, from cephadroxyl, so from droxyl we can say hydroxy. So it also has a hydroxy OH group in its structure. Okay. Now moving forward towards the next drug, that is cefuroxime. Now cefuroxime is the second generation drug. Now we are going towards the higher generation. Okay. Now second generation cephalosporin drug. Now it can be taken through IV and it can also be taken through oral. Now we can only take it orally if it is converted to its prodrug form. Now prodrug cephalosporin exitus. Now it is the prodrug of cefuroxime as it is acid unstable. So we have to convert it into its prodrug so that it can become acid stable. Okay. Now it is effective against the gram-positive bacteria and the gram-negative rods. Now moving towards its structure, now it has a beta-lactam ring joined with the dihydrothiazine ring. Okay, now at third position we have OCONH2 group attached, and at seventh position, now here if we look at its name, we have oxime. So what is oxime? C double bond N OH. Now this is the oxime group. So here we have a oxime group in its structure along with a furan ring, a heterocyclic ring. Okay. Now moving forward towards the next structure, that is the cephexim. Okay. Now cephexim, it is the third generation drug. Now the higher generation drug, it is orally active, acid stable. Okay. Now it is effective against the gram positive bacteria and some gram negative bacteria too, and used for the typhoid and UTI. Now this structure, now this name cephexim, now it also has the oxime in its name. So when we move on to its structure, now it has a beta-lactam ring that is fused with the dihydrothiazine ring. At fourth position we have a carboxylic acid again. At third position we have a alkene attached. Okay, that is ethylene attached, we can say. Now at seventh position with amide we again have a oxime like group and a heterocyclic ring. Okay, so cephexim. Now moving forward towards the next drug. Now this is an important drug. This is the fifth generation cephalosporin drug, the newest generation drug. Now this particular drug, it is taken through IV, and it is the only cephalosporin drug that is effective against the methicillin resistant Staphylococcus aureus. Okay, now all the beta-lactam drug were not working for this particular bacteria, but this ceftriaxone, okay, the ceftriaxone, this drug, that is the fifth generation cephalosporin drug, is effective against MRSA. Okay, so you have to remember it. Now it is taken through the IV route. Now moving to its structure, again we have a cephalosporin main moiety, that is the Cepham. Now here beta-lactam ring that is joined with the dihydrothiazine ring, carboxylic acid here at fourth position. At third position again, now this is also a Zwitter ion. It also has a positive and a negative charge in its structure. At third position we have a heterocyclic ring attached. Again at seventh position with amide group we are again attached with the side chain, that is the heterocyclic ring. It has a very bulky side chain. Okay, the fifth generation cephalosporin. Now moving forward towards the next beta-lactam antibiotics, that is the beta-lactamase inhibitor. Now what is this beta-lactamase? Now this beta-lactamase is basically an enzyme that is released by the bacteria that can inhibit the beta-lactam ring. Okay, now this beta-lactamase inhibitor inhibit this beta-lactam ring. Okay, so now these are the compounds which inhibit the beta-lactam enzyme, lactamase enzyme, and they do not have their action by itself. They do not have any therapeutic activity of themselves, but they are combined with the other antibiotics to show their activity or to extend the spectrum of the other antibiotic. Okay, now the first is the clavulanic acid. Now the clavulanic acid, this is the beta-lactamase inhibitor, and it comes under the class of suicide inhibitors. Okay, now it is a irreversible binding, it has a irreversible binding, and it contains a beta-lactam ring with no therapeutic activity or no antibacterial activity of its own. Okay, now this here is the structure of clavulanic acid. Now here we have a beta-lactam ring that is joined with 𝙂𝙎𝙎𝙎𝙬 ring. Okay, now here again we have a carboxylic acid attached, and here at side chain we have a ring attached with double bond COH. Okay, now moving forward towards the next drug, that is sulbactam. Now you have to remember, now sulbactam also have a unique property that, as we discussed, that beta-lactamase inhibitor, they do not have its own activity by itself. They do not have their any property. They have to combine with some drug or some antibiotic to show their activity. But the sulbactam, it has its own intrinsic activity against the Acinetobacter. Okay, now this sulbactam here has an own intrinsic activity. Now it is also a beta-lactamase inhibitor. Now talking about its structure, now its structure is almost similar to penicillin, very similar. Now it has a beta-lactam ring. Okay, it has a thiazolidine ring. Okay, a 5-membered ring with 1 sulfur and 1 nitrogen here. Now here again we have 2CH3 or 2-methyl group attached at the second position. At third position we have a carboxylic group attached, and here the sulfur is in the oxidized form. Okay, now moving forward towards the next class of the beta-lactam ring, that beta-lactam antibiotic, that is the monobactam. Now monobactam, by name we can say mono. Mono means single. So in this, the beta-lactam ring is not fused with any other ring or any other heterocyclic ring. There is no fusion in this particular antibiotics. They act against the gram-negative bacteria only. So they are not effective against the gram-positive bacteria. They are only effective against gram-negative bacteria, and there is no fusion in its structure. Now these are used in the penicillin allergic patients. Now when we were studying about the penicillins, now there I told you that taking penicillin, it is very common that people may get allergies, allergic reactions. Now this monobactam can be used whenever a patient or an individual have a penicillin allergy. Okay, now Aztreonam. Aztreonam is a type of monobactam which is effective against the gram-negative bacteria and have no activity for the gram-positive bacteria. Okay, now here is the structure of the Aztreonam. Now here we have a beta-lactam ring, and it has a no fusion with any ring. Okay, now here we have SO3H group attached and a CH3 group attached, and with amide group we have a bulky group attached with a heterocyclic ring. Now moving forward towards the last beta-lactam antibiotic, that is the carbapenem. Okay, now this carbapenem is a beta-lactam antibiotic, and it has a carbapenem nucleus in its structure. Okay, now first here is the thenamycin. Okay, now this 𝘂𝑉, it is a natural carbapenem. Now, natural carbapenem antibiotic. Now, this particular antibiotic, this particular carbapenem is not clinically stable. Now, it is unstable. Now, why is it unstable? Because of its structure. Now, in its structure, it has a free NH2 group here. Now, due to this NH2 group, it has some instability. Okay, so it is not clinically used, and it contains a hydroxyethyl side chain. Now, this hydroxyethyl side chain is responsible for its resistance against the beta-lactamase. Okay, now this particular hydroxyethyl side chain is responsible for its resistance against the beta-lactamase. Okay, now imipenem is the next carbapenem. Now, this imipenem is the derivative of this 𝘂𝑉 only. Okay, now this 𝘂𝑉 was unstable. Now, this imipenem is stable. And why it is stable? As due to this NH2 group, it was unstable. Now, here we have modified this NH2 group here in this imipenem. So, now it is an stable structure, a stable carbapenem. Okay, now this particular carbapenem is effective against both the gram-negative bacteria also and the gram-positive bacteria also. It has a broad spectrum of activity. Okay, now this imipenem is not given alone. It is given in the combination with cilastatin. Now, why? Now, this cilastatin, why it is given? Now, this particular carbapenem, that is imipenem, it get killed by the enzyme in the kidney, that is the renal dehydropeptidase. Now, to save the killing from this particular enzyme in kidney, we combine this imipenem with cilastatin. Okay, so this is all about the beta-lactam antibiotics. Okay, hope you understood. Now, in next video, we will start with the next antibiotics, that is sulfonamides. Okay, thank you.